Hello, welcome to VTU EduSat classes on automata theory and computability. So today is my last class of the second module and we will be discussing on regular and non-regular languages. So myself Dr. Girijamma H.A. working as a professor in the Department of Computer Science and Engineering at RNS Institute of Technology, Bangalore. So for any of the queries, so you can reach to me to the displayed mail ID. So today we will be discussing on showing that a language is not regular. Okay. So all these classes we have discussed the regular languages, and then so today we will prove using the pumping theorem how a language will not be regular, and then so we will be discussing on long strings force repeated states. Okay. So next we will be discussing on a very important theorem, that is the pumping theorem for regular languages. So next we will be discussing some of the examples of pumping theorem. Next, so using closure properties also you can prove that the language is not regular. So that we will be discussing, and we will be discussing at the last some of the exercise problems. So lastly, so I will summarize what all we have discussed in the second module. So first, showing that a language is not regular. Okay. So we can show a language is regular by exhibiting a regular expression or an finite state machine or a finite list of equivalence classes or a regular grammar, or by using the closure properties of regular languages. Okay. So there are many ways to show that a language is regular, but how shall we show a language is not regular? Every language L can be accepted by an finite state machine with finite number of states. Okay. So if L is infinite, then there must be at least one loop in M. Okay. So this is what so we will be proving. So next, showing that a language is not regular. Okay. So we will consider here the two FSMs displayed here. Okay. So if you see the first in figure A, so this is a finite state machine which is having one loop. Okay. So it can accept a infinite number of strings. So not only it accepts B A A B, it accepts B A B A B, B A B B A A B. So it can accept very long length string. Okay. So whereas if you observe here in the second figure, here also it is also having a loop. Okay. But it having a loop with epsilon transitions. So it can accept only the string AAB. Okay. So it cannot accept strings more than that. Okay. So the length should be only AAB, more than that so it cannot accept, but always we know that for every epsilon non-deterministic finite state machine, okay, so there exists an equivalent finite state machine. So for our next consideration we will be speaking only about DFSMs and will be not speaking about NDFSM with epsilon transitions. Okay. So that is why, so here we will not consider NDFSM. So in showing the languages are not regular, because we know that for every NDFSM there exists an equivalent DFSM. Okay. So we will consider only the FSMs. Okay. So if you observe here, this accepts strings of long length, whereas this accepts strings of length 3. Next we will move to the important theorem, that is long strings force repeated states. Okay. So here, so let M equals K sigma delta S A be any deterministic finite state machine, and if M accepts any string of length K greater of length equal to K or greater, then the string will force M to visit some state more than once. Okay. So this principle or this theorem is based on a pigeonhole principle. Okay. So, we know the pigeonhole principle, that if there are n pigeons and m pigeonholes, okay, and pigeons are more than the pigeonholes, okay, then at least one pigeonhole will be shared by more than one pigeons. The same concept we have used, that is, if the length of the string is more than the number of states, then at least one times it should enter into a loop. That is, if the length of the string, for example, the string which belonging to that language if you take, and if you take the number of states. So, if the string length is greater, then somewhere else it have repetitions. Okay. So, the proof is that the same which is based on the pigeonhole principle. Okay. So, here the theorem states that we are assuming a finite state machine, and if m accepts any string of length k. What is k? K is the number of states or greater. Okay. So, string we can take w. If w is greater than k number of states, then the string will force m to visit some states more than once. So, that means more than once, if a state has to be repeated, it has to enter a loop. Okay. So, here the proof m must start in one of its states. Each time it reads an input character, it visits some states. So, in processing a string of length n, m creates a total n plus 1 state visits. Okay. So, if n plus 1 is greater than the number of states, that is k, then by the pigeonhole principle, some state must get more than one visit. Okay. So, that is, so if n is greater than k, then m must visit at least one state more than once. Okay. So, next we will be discussing the pumping theorem, which is based on this concept. Okay. So, this is very important, and this will be using in proving the language is not regular. The same example we will take. Okay. So, here now consider the m loop which we have discussed earlier. Okay. So, it consists like this. So, even though here it has 5 states, so it can accept the string of length k equals of length 6 or also of 7, 8, in between it can have many b's. Okay. So, that means here, so what does, according to the previous theorem, so it has traversed to a state more than once. Okay. So, if the length of the string, okay, suppose 1, 2, 3, 5 states are there, and if the string is, let me take BA, BB, BAB. Okay. So, here the length is 7. So, it must be traversed at least 2 times. Okay. So, the same concept we will be using in pumping theorem, that is, we can pump any b's and get a similar result. Okay. So, here in the middle, if you have any number of b's, it can be pumped here. So, hence the name pumping theorem. Okay. So, next we will discuss the very important theorem, that is the pumping theorem for regular languages. So, what does it states is, if L is regular language, then there exists a k which is greater than or equal to 1, and for all strings w which belongs to L, where length of w is greater than or equal to k, then there exists x, y, z such that w equals x, y, z, and length of x, y is less than or equal to k, and y is not equal to epsilon, and for all q, so x, y to the power of q, z belongs to L. Okay. So, this statement you have to remember, because this is the statement we will be using to solve the problems, or that is in the applications of pumping lemma, to show the language of is not regular. So, we will be using this. So, I will repeat this. If language is regular, then okay, there exists a k which is greater than or equal to 1, such that for all strings w which belongs to L. Okay. So, you take any string which belong to the language, and you split w in the form of x, y, z, such that length of the x, y is less than or equal to k, and y it should not be equal to epsilon, and then q is greater than or equal to 0, then in such case x y to the power of q z, it should belong to the L. Okay. So, this is the statement of pumping theorem. Okay. So, now we will proceed for proof. So, if L is regular, then it is accepted by some deterministic finite state machine M equals K sigma delta S and then A. Okay. So, let K be number of states. Okay. So, how many number of states? So, that you can take it as K. Next, W be any string in L of length K or greater. So, by previous theorem, to accept W, M must traverse some loop at least once. Okay. So, we can carve W up and assign the name Y to the first substring to drive M through a loop. Then X is the part of W that precedes Y and Z is the part that follows Y. So, here he is saying that, so you can split W in the form of X, Y, Z such that the length of the X, Y, it should be less than K, less than or equal to K, and Y it should not be equal to epsilon, and such that X, Y to the power Q, Z, it should belong to the L. Okay. So, now we show that each of the last three conditions must hold. Okay. So, those three conditions, what are those three conditions? When you split in the form of x, y, z, so the length of x, y, it should be less than or equal to k, and M must not traverse through a loop, and it can read k minus 1 characters without revisiting any states, and kth character will take M to a state visited before, and next case is y not equal to epsilon. Since here M is deterministic, there are no loops traversed by epsilon. Okay. So, here that is why we are considering all deterministic FSM, and for all q greater than or equal to 0, x y to the power q z, which should belong to the L, that is y can be pumped out once and the resulting string must be in L. Okay. So, this is the proof of the pumping theorem. So, now in the problems, so using this theorem, pumping theorem, you should prove that the language is not regular. Okay. So, we know that pumping theorem, it holds good for a regular language. So, always we will prove the problems in a contradiction method. So, I will clearly listed the steps. So, you can follow the steps and you can prove any language is the given language. If it is not regular, then you can prove it is not regular. So, what we will prove in a contradiction method. Okay. So, in always contradiction method, first we will assume that it is regular. Okay. So, first we will assume the given language is regular, then we will apply the pumping theorem for the given language, because if it is a regular language, then your pumping theorem should holds good. Then you choose a string W where W belongs to L and length of the W is greater than or equal to K. Okay. Then you split the W into x, y, z such that x, y is less than K and y not equal to epsilon. Then choose a value for Q such that x y to the power of q z is not in L. Okay. So, you can choose any value, either q may be 0, 2, anything you can choose, and then you can prove that it is not in L. Okay. So, when it is not in L, what your assumption is L to be regular. So, our assumption is wrong, hence the given language is not regular. Okay. So, we follow all these 6 steps and then we will show the language is not regular. For example, so by using the pumping theorem, we will show that the language a power n, b power n is not regular. Okay. So, let L be the language which is defined by a power n, b power n, and which is equal to n number of a's followed by n number of b's for all n greater than or equal to 0. Okay. So, now using pumping theorem, you should prove that this language is not regular. Okay. So, what we will do is, so first we will take any string which is we will take any string and then, so let w equals, I will write a k and then b k. Okay. So, a to the power of k and b to the power of k, such that length of the w is equal to now 2k. Okay. So, why a to the power k, b to the power k is because the length of the string, it should be greater than k. Okay. So, that is why now it is 2k. Now, so we will split w in the form of x, y and z. Okay. So, such that length of the x, y, it should be less than or equal to k and y not equal to epsilon. Okay. And then for all q greater than a, x, y to the power of q, z which belongs to the L. Okay. So, q, it can take the values 0, 1, 2, etc. So, this theorem now you should apply. Okay. So, now split in the form of x, y, z. So, what is the given string? The given language is n number of a's followed by n number of b's. So, you can take first, let me take n number of a's and then separator, then you have some b's. Okay. So, let us assume that this as k and this as k. Now, you choose y, x, y, z. Okay. So, length of the x, y should be less than k. So, I am choosing y as a to the power p. That means, out of k a's, some a's I am choosing as a part of y. Okay. So, your language will become a to the power of k minus p, then b to the power of k. Okay. So, why a to the power of k minus p is because x, y, z. Okay. So, y, it is a part of k a's. So, out of k a's, I am choosing a to the power of p a's as number of a's. Okay. So, this k a's, so it will be some p a's will be in y part and remaining will be in x part. Okay. And all this will be in z part. So, now your language consists like this: a to the power of k minus p, b to the power of k. So, if you take p value as 2, okay, then you will be having less number of a's than b's, which your language will not belong to the language. Your string will not belong to the language. So, you need not take the string which I have taken it. So, you can show it in a different way. So, this is one way of showing it. So, next we will proceed for one more example. Okay. So, like this, in the textbook he has given 3 cases. You can show for any case and then you can prove that it is not regular. So, in a similar way, let us apply the pumping theorem. So, we will apply the pumping theorem for balanced parenthesis language is not regular. So, what is that balanced parenthesis? Whenever you are using a parenthesis in expression, left parenthesis should always be balanced with right parenthesis. Okay. So, that is why, so your language is defined as balance, which is given by w, which belongs to left and right parenthesis, and then the parentheses are balanced. Okay. So, now, so let us prove this using the pumping theorem. First, let us split the string into x, y, z. Okay. So, balanced parenthesis you can take like this. If there are 3 left parentheses and then there should be 3 right parentheses. Okay. So, I have taken the case of this one. So, what W will be, let me take, there are left parenthesis to the power k, and then similarly it should have right parenthesis to the power k. How many number of left parentheses you have used, those many right parentheses should be there, then only the parentheses are balanced. Okay. So, now what will be the length of the W? Length of the W is k plus k, it is 2k. Okay. So, now, so you should split this W in the form of x, y, z such that x, y, the length of x, y, it should be less than or equal to k, and y, it should not be equal to epsilon, and then x, y to the power of p, z belongs to L for all p values 0, 1, 2, 3. This is pumping lemma theorem. Now, so you have taken this expression so that we can split this in the form of x, y, z as in the previous theorem. So, let me take the value of y. Okay. Let y equals a to the power of p. Okay. So, that means, so first here you will be having, let me say, some k left parenthesis. So, afterwards again you will be having some k right parenthesis, in between whatever it may be, we are least bothered, just we have to match the left and right. Okay. So, out of this k left parenthesis, I have assumed y as left parenthesis to the power p, not, sorry, this is not a, this is left parenthesis to the power p. So, your expression will be left parenthesis k minus p and then right parenthesis to the power k. Okay. So, now what happens? You have p number of left parenthesis less than right parenthesis. So, this language does not belong to L. So, what we have assumed that language is regular is false. Okay. So, in this way, so you can prove that, you can take any example. For a simple, I have taken just left and right. Okay. So, you can take anything whichever is convenient. Okay. So, any string which belongs to this language. Okay. So, next last example, we will take the even palindrome language is not regular. So, what is WWR? W is any string which belongs to AB and WR is the reversal. Here we are restricting ourselves to the even length. That means, so W should be even length, then WR will also be even length, then total palindrome will be of even length. Okay. So, pal even is the language of even length palindrome. Okay. So, let us prove this example. So, let us take one example where W equals AK, BK and BK followed by AK. So, why you should take AK, BK? Because W is any string of which belongs to AB. I have taken first k number of A's followed by k number of B's. So, the reversing if you take, it will be first k number of B's followed by k number of A's. So, you can take any string. Since if I stick A and B in random, okay, it is difficult to prove. I have taken first k number of A's followed by k number of B. So, this will be the reversal. And what will be the length of the W? Length of the W is 4k. There are 4 k's. So, k and W is in L. Now, you should split W in the length in the form x, y, z. Okay. So, let me take y equals a to the power of p. Okay. So, in the first a out of k is, so a to the power of p's I am taking it as y. So, in the x y z, so your expression will be a to the power of k plus p followed with b to the power of k followed by b to the power of k followed by a to the power of k. Okay. So, then what happens if p is odd? Okay. So, if p is odd, we know that k is even. So, odd plus even, it will be always odd. That means, you will be having more number of a's here, and here you will be having even length. So, this will be not a palindrome. That means, whatever the string we have taken, it does not belongs to the L, and hence whatever we have assumed is wrong. Hence, the given language pal even is not valid. Okay, like this. So, you can prove that any language is not regular. So, you need not take whatever the examples have taken. So, you can take any examples and then just you apply the pumping theorem. So, you should remember that while splitting the length of the xy, it should be less than k, and y it should not be equal to epsilon, and you should show any string, one string also which does not belong, that is x y to the power of p z, which does not belongs to L, then the language is not regular. So, we know like this. So, there are in the textbooks plenty of problems are there. So, you can solve using the pumping theorem. Next, the closure properties. So, till now we have seen the closure properties for proving the language is regular. Okay. So, now using these closure properties, you can show the language is not regular. Okay. So, that is using intersection to force order constraints. Okay. So, let us assume L equals W, which belongs to A B star for all A W. Okay. So, that is number of A's in a W is equal to the number of B's in W, that is the language given. If L were given, okay, if L it is regular, then L dash equals L intersection A star B star would also be regular, but L dash equals, okay, so A power n B power n. So, for all n greater than or equal to 0, which we have already shown is not regular. Hence, so the given language is not regular, where the number of A's in a string is equal to the number of A's in a string, because closure properties holds good for regular languages, and since here this is not regular, so this will not be regular. So, you can show this way also the languages are not regular, and so L isn't either. So, the conclusion is we are proving the language L is not regular by already known fact that L dash is not regular. So, using the closure properties also you can prove that the language is not regular. So, next let us see some of the exercise problems. Okay. At the end of the chapter, there are plenty of problems already have taken up on regular expressions and then regular grammars. So, this is on the last chapter, that is the 6th chapter on regular and non-regular languages. Here he will be giving the language, and you should state that whether the language is regular or not. Okay. So, for example, the given language is A power I B to the power of j for ij greater than or equal to 0 and I plus j is 5. Okay. So, here clearly I plus j is 5, it is regular and it is a simple finite state machine with 5 states, just counts the total number of characters. Okay. So, hence I plus j is finite. Okay. So, you can design a FSM, hence the given language is regular. Next problem is A to the power I B to the power j, where ij is greater than or equal to 0 and I minus j is 5. So, this is not regular. Okay. Why? Because L consists of all the strings of the form A star B star, where number of A's is 5 more than the number of B's, and it is difficult to keep track. And we can now show L is not regular by pumping, that is, you can split W in the form of A to the power of k plus 5. Why k plus 5? Because here I minus j is 5. Okay. So, if it is I minus j is 5, then you should have k 5 number of A's more than B. Okay. So, that is why. So, you can split W in the form of A to the power of k plus 5 B followed with Bk, and then split xy in the form of like this. Then, so you can choose the value of y. Y can be chosen as A to the power of p, which comes here in this part. So, here you will be having A k plus 5 minus p followed with b to the power of k, which is not in L. Hence, the number of A's is less than 5 more than number of B's. Hence, the given language is not regular. Okay. So, here we are proving it is not regular by using the pumping theorem. So, next we will take the simple problem, that is a to the power I, b to the power j, where ij is greater than or equal to 0 and I minus j is mod 5 equal to 0. That means it should be a I minus j, it should be a multiple of 5, then only you will be getting the remainder as 0. Okay. So, if this is possible only if and only if I is a multiple of j. Okay. So, L can be accepted by a straightforward FSM that counts A's mod 5, and similarly then it count B's and accepts if and only if the number of the two counts are equal. Okay. So, this is regular and you can design an FSM for this. Next, we will consider A to the power I, B to the power of j, where ij is less than or equal to 0 to 2000. Okay. So, since here it is finite, the given problem is regular and you can design the FSM. Next, W belongs to y n to the power of n star, and W contains 2 y's and at the most 2 n's. Okay. So, this is regular. Always we have designed in the regular expressions, we can write the regular expressions and you can design the FSMs. At least 2, there can be more than 2 y's, but at least 2 and at most 2 n's. Okay. So, this you can design it and hence it is regular. And showing, so in the last class, so we were discussing about the closure properties. Okay. So, we have not discussed the reverse method. Okay. How to take the reversing. Okay. Let us give the method for reversing the language. Okay. So, if W, how you can prove that the reverse of L is also closed. That means, so you should show that when you reverse a language, it is regular. So, we will show by construction method. So, what is that method? So, we will first assume the M to be a FSM that accepts L, then initially M dash be M, then reverse the direction of every transition in M dash. Okay. So, just if it is going from state 1 to 2, so you should make it from as a going from state 2 to 1, reverse the direction, and you construct a new state Q, making it the start state of M dash. Okay. So, you should construct a new start state and then to make it as M dash. Next, so you create an epsilon transition from Q to every state that was an accepting state in M. Then whatever the FSM you are getting it, so it will be accepting the reversed language. So, in the last class, so we have seen if the string is ABB, then the reversing of it will be BBA. So, next M dash, it will be having a single accepting state and the start state of M. Okay. So, in a similar way, so you can also prove under substitution, letter substitution, or also we will call it as an homomorphism. So, this in the last class we have taken up the examples, but we have not proved the language is regular. Okay. So, when you apply the homomorphism or the letter substitution, you should show the language is regular. So, this can also be proved by construction method. So, let sub be any function from sigma 1 to sigma star, and let sub be a letter substitution from L1 to L2. This already we have discussed this, and we can do with the FSMs. So, if L is regular, then it should be accepted by DFSM. Okay. So, now what you should do is, from the L we construct a machine M dash, and to accept letter of sub L. Okay. So, wherever the symbols of sigma 1 is there, just you replace with that homomorphism. Okay. So, next, and then change the M dash as follows. So, for each arc in M dash labeled x, for any x change the label to sub of x. So, for each letter, so you will be defining the sub function. Okay. So, that you can design it, you can write it on the transitions. So, M dash will accept exactly the strings accepted by M, except if it is M accepted some character, then M dash will also accept S of x. So, this is how, so you can do the by the construction method. So, you can prove that the closure under letter substitution is regular. So, this is the end of the second module. So, let us see or summarize what all the important topics we have discussed in the module 2. Okay. So, module 2, it is very important in the part of exam. Okay. So, you will be having 2 questions. So, out of which, so you have to do answer 1. So, majority of the questions, one question will be on regular expressions. So, that is, they can ask either the definition or for any given language writing the regular expression. Okay. So, this is very important. So far we have discussed some 15 to 20 examples for a given language how to write the regular expression. So, you can for any language, so you practice some regular expressions to write down. So, next is about the for a given regular expression how to construct the FSM. Okay. So, this is the Clean's theorem first part. So, this we have already discussed by the construction method, and we constructed an FSM with non-deterministic and with epsilon transitions. So, we know that for a non-deterministic finite state machine there exists an equivalent FSM. So, you can there exists an equivalent DFSM. So, always here we will be constructing then FSM with epsilon transitions. So, next part what we have seen is FSM to RE, that is, if a FSM finite state machine is there, how to build the regular expression. Okay. So, here we discuss the 2 methods. So, one is the heuristic method and the another one is using 2 subroutines, that is the standardized and build regex. Okay. So, those 2 subroutines you can use and you can construct the regular expression for the any FSM. So, out of these 2, so you will be having the problems. So, they will be giving the regular expression and they will be asking you to write the equivalent FSM, and similarly here they will be giving the finite state, any finite state machines. So, by ripping out the states. Okay. So, keeping only the start state and the accepting state. So, you should find the equivalent regular expression. So, already in my second class, so I have discussed many of the problems. So, those problems you can solve and then so you can be thorough. Next, in the third class, so we have discussed the writing of the regular expressions for password, IP address, okay, for a legal password, IP address, floating point number, decimal number, all those things. Okay. So, we have written the regular expression in different notations. So, that is very important. So, in the exam they can ask. And so, in the last, so we have discussed the applications of regular expressions. Regular expressions are very popular and they are used in many of the scripting languages, web searching. So, there are plenty of applications discussed. Okay. So, those you should be thorough. Next off is building the DFSM. Okay. So, we have built a DFSM for cat, cab, mat. Okay. So, similarly for any of the keywords you can build a DFSM. Here clearly we have given the method for when the path dies. Okay. So, that means suppose if cat is not there, then what to do. So, that complete explanation using build keyword algorithm. So, you can build it. Next is manipulating and simplifying the regular expressions. So, here we discuss the three identities, okay, of union, concatenation and star closure, and we discussed how regular expressions can be simplified. Okay. So, when there is a long regular expression, it can be replaced with simple regular expressions by using the identities. Okay. So, this is also very important. Next, we discuss the regular grammars. So, as we all know, so like regular grammars, as like regular expressions and finite state machines. So, even regular grammars are used to define the regular languages, and then so we discussed how to convert the grammar to equivalent FSM. Okay. Or in the exam, so you may get the problems of either type, either they will give the grammar, they will ask you to write the FSM, or they may give the FSM and they may ask you to write the grammar. Both the algorithms and problems are discussed here. So, next comes the regular and non-regular languages. Okay. So, here we discussed what languages are regular and how you will come to know language is regular. Okay. So, these all things we have discussed this. Next is about the closure. In the last class we have discussed the closure properties of regular languages. So, we know that regular languages are closed under union, intersection, concatenation, then complement, letter substitution. With all these, so you can show, and we have worked with many examples also, all you can prove by the construction method. Okay. So, next very important is the pumping theorem. Okay. So, there are many features to show that the language is regular, but to prove that the language is not regular, always you can use the pumping theorem. Okay. So, from the exam point of view, this pumping theorem is very important. State and prove pumping theorem. So, normally they will ask. Next, the application of pumping theorem. So, once the theorem is learnt, so application of theorem means how you can apply the pumping theorem. Okay. So, we discussed some a power n, b power n, then WWR, okay, and similarly even length palindromes. So, likewise you can apply the pumping theorem for many of the problems. Okay. So, these all things and some exercise problems of chapter 6, 7, 8. So, I have tried my level best to cover the maximum and important portions. Okay. So, if you have any queries, so you can reach me at the displayed mail ID. So, this is my mail ID girijakaSal@gmail.com. Okay. So, thank you one and all.